Working. All right, thanks for the introduction. Thanks everybody for coming here. I hope you're having a good day, enjoying this nice day in Berlin and have a good conference so far. I'm Stephan. I'm talking about the stream processor as a database here with Apache Flink. And yeah, let's get started. So I always start my talks with this quote just to basically get set the stage for the kind of twist of stream processing that I'm talking about and the way we're thinking about stream processing with Flink. Because a lot of people still think stream processing is something that is tailored towards a niche of low latency applications. And what I really have in mind when I say stream processing here, and what's kind of the paradigm behind the way Flink is developing, is that stream processing is actually not just like a low latency real-time thing. It's really a paradigm for continuous processing on continuous data. Continuous data being basically all data that is not dumped at you in a terabyte at an instant, but is really produced over time. You know, logs, sensors, everything that gets appended and created over time, accumulates to very large amounts, but is created over time. And you're actually processing this in a continuous fashion, following this continuous paradigm. This is a very nice paradigm that solves many problems, and that's really what Flink is about. I'm going to just spend a minute or two on a Flink 101 for those that are not too familiar with the system so far, and then dive into the stream processor as a database. So Apache Flink at its core is a streaming data flow system for streaming applications. So the bottom layer is the streaming data flow runtime. It's a runtime of operators and streams connected in a directed acyclic graph. That moves data between parallel instances, processes it, transforms it, produces streams, consumes streams. And on top of that runtime, we've built two APIs, a stream processing API and a batch processing API. The batch processing API also executes on the stream processor, so it's really basically interpreting batch as a special case of streaming and running it on a streaming runtime. We currently have two different APIs because the batch processing API has a bit of extra semantics and syntactic sugar for cases that just become a little simpler if you think of static data sets rather than continuous data sets. And on top of these two APIs, there's a bunch of libraries, for example, for complex event processing, for graphs or machine learning. All right, if you're using Flink, what you're basically doing is you're writing a functional program in either the Java or the Scala APIs. You're working with data streams, you're applying functional transformations like maps. You can reorganize data, you can apply windows and then do aggregation functions and so on. So this functional program gets transformed into a data flow graph, and the data flow graph gets sent to the distributed cluster for execution. The kind of core pillars of Flink, or at least of the streaming side. So I'm going to focus very much on the streaming side. I mentioned it has a dataset API for processing of static datasets or bounded datasets, but I'm going to focus very much on the streaming side today. So the four pillars of this streaming side, which actually I think make Flink the nice and versatile tool that it is today, are those. It's a true stream processor with support for event times, data processing, and a bunch of nice APIs and libraries. And those four in combination, each one actually brings some very good aspects with it, but all of these four together actually make a very, very strong and powerful combination. And today, the focus I have in this talk will be mainly around the stateful side, the blue or violet box in the bottom left corner. So to motivate why we even want to think about this architecture, the stream processor as a database, let's actually go through a very simple or very classic use case, maybe one of the most classic use cases for stream processing that you can have. And that is creating real-time counters and aggregates. So think about the following. You're a system, or you're a company that has a stream of events, of user interactions, and you just want to create some real-time aggregates, be that to expose them in a dashboard, or be that just to have a data service that you want to offer to your customers. That, for example, let's say you're Twitter and you want to offer to somebody that they can look at how often have people interacted with my tweets. Very, very simple thing. it may sound like it's the simplest thing you can possibly do with stream processing, but if you actually want to solve this end to end, everything, the latency, scale it very large, have it run very reliably, and yet efficiently, it's a very hard thing that people are still sort of struggling with. And over the course of this talk, I'm going to actually show you what the next kind of obstacle is we're getting out of the way here. So the architecture to implement this is it's a very, very classic streaming architecture. You start off with basically collecting the events that you want to analyze. You log them in something like Kafka. You compute the aggregates in Flink, and then you expose it somewhere in one of the many databases or key value stores. Pick your favorite. The implementation of the processing job is also fairly simple. If you look at it, this is an example from Flink's Scala APIs. On the top line, we're simply defining ourselves a simple type with which we're going to work with, basically impressions with an ID and the number of impressions, and then we're creating our stream, reading from Kafka. We're going to filter and transform the impressions a bit, and then the bottom lines actually show that they're grouped by ID, and then we sum up the impressions in time windows of 1 hour. So far, so good. To help you sort of get the structure of this program, here's kind of the data flow representation of what this program boils down to. So I've drawn it with a parallelism of 2, but I guess you can generalize from there. It can be way more parallel than just 2 threads, right? Starting from Kafka, first running through the filter, running through the map. You're shuffling across the network when you reorganize it by the key, by the ID, and then building windows, summing it up, and writing it somewhere so somebody can actually look at the aggregates. That's the basic structure of the job. If we run this putting it all together, if we run this in the infrastructure, it's going to look somewhat like that, right? Data from Kafka, there's going to be only 2 operators in the runtime in Flink because it's going to condense a lot of the operators together. For example, the source, the filter, and the map are going to become one thing. The windows and the sink are going to become one thing. It's going to run in multiple parallel instances. And the data is written, just put the Redis icon here. It's the one that we used in this example, but it could be any other key value store, actually. Yeah, and the results are exposed via key value store, and the queries go against that key value store, right? So if you say, okay, let me see how many people have interacted so far with my tweet with that ID, you just pick this up from the key value store. So remember now that the aggregates that we're computing were like in hourly windows, right? So you'd sort of aggregate data per hour. And if you would only ever write it to the key value store after the hour's up, after the full window is up, you'd not have a very, very real-time, up-to-date view of your statistics in the key value store because, well, you could never actually look at any in-flight aggregates or so. You could only ever see what is the result of the window. Especially when you use the event time window functionality in Flink, and it sort of compensates for out-of-order events and for some late events, then the hour can be computed actually even quite a bit later than the full hour is up. So what you probably want to do in this use case is add something like, in addition to the event time watermark trigger, that is Flink's internal mechanism to figure out when is an event time hour full, add something like a periodic trigger that just periodically flushes the current aggregates into the key value store, so you could actually pick them up. That is interestingly not a very, let's say, exotic way of doing it. A few months back, Yahoo published a streaming benchmark, and that is pretty much exactly what the sample application in the streaming benchmark was doing. It was computing windows. I think in their case it was just like 10-second windows, and it was computing them inside the stream processor like that, and every second exposing them to an outside key value store, and allowing you to basically query the up to the second accurate data. So, looking at this very simple design, it may not, it may feel a little funky. You flush all these early aggregates always into Redis, and then you actually at some point do the final ones and can close the window and move on to the next hour. But apparently that's what people are doing. So let's actually look how well it does. And looking at how well it does, we're going to look at 3 dimensions: latency, throughput, and the scalability with respect to how many aggregates are we actually looking at. So for the latency, I already mentioned that Yahoo's benchmark was pretty much looking at exactly that use case. So for latency, let me just cite their benchmark. There was sort of the summary graph from the experiments they did across Flink, Storm, and Spark. The versions are, I think, all like half a year back or so, but it's not like something very, very fundamentally changed there. So the ballparks, at least, are still the same. And it's kind of a throughput latency trade-off, and you can see the throughput goes to something like 180,000 events per second, and then the latency is anywhere between, for Flink and Storm in the second range. For Spark, it actually goes up. So let's assume latency is actually doing okay in this case. The throughput, if we look at the throughput, 180,000 elements that's something. It's okay for a lot of operations, but it's actually not really the limit of this kind of application. So we actually did some experiments where we looked into the throughput of exactly that job and just pushed it a little further. These experiments were actually done on a cluster at Twitter. It had the interesting setup that the storage cluster and the compute cluster were separate. So there was inside each cluster they had 10 gigabit Ethernet connections, but between the cluster only 1 gigabit Ethernet connections. So you could actually see that if you look at the implementation in Flink at least, reading the data from Kafka and the setup as I explained it earlier sort of hit a bottleneck here. That bottleneck is interestingly not up to Kafka. It's really because the cross-cluster link was just saturated at some point in time. If actually both were running with a 10 gigabit interconnect, you could probably go much further there. So what this was basically doing, it was sort of using a trick to move the data directly into the cluster and read it basically within the same cluster with 10 gigabit link. And you can see that the Yahoo benchmark stops somewhere at 180,000 events per second. But you can actually push this if you have a decent network to quite a lot. This was running on 10 machines, so to 15 million elements per second. So, I mean, throughput seems to be okay in general in that case that they suggested in this benchmark. But the most interesting dimension, actually, that is the motivation for this kind of work I'm presenting here is the third dimension, looking at how does it do with a number of keys. So if you actually look at this Yahoo benchmark very closely, you'll actually see that it only keeps 100 counters. So the motivation was tracking the interactions with advertising campaigns, and they were assuming there were never more than 100 advertising campaigns, so we just track 100 counters. So what this means actually is that every second 100 counters and keys are sort of flushed to the key value store, which doesn't seem like a lot of work. It doesn't seem like that should pose a challenge for many key value stores. So on the other hand, it doesn't really reflect a lot of real-world use cases, right? 100 aggregates are definitely on the lower end of what people usually have. So going back to our motivating example, if we want to actually count the impressions over tweets, right, then the number of keys you will have within this hourly window are actually large. I think concretely in the example that we did on tweet impressions was 500 million keys per hour, which means that actually every second multiple hundred thousands up to a million keys are updated. And if we actually look at how does this particular setup perform with these different keys, that dimension makes a huge difference, right? If you flush 100 keys per second, that's going to be fine. If you may have to flush a million or hundreds of thousands of keys per second, then you immediately hit a throughput bottleneck. So the bottleneck in the key value store, the bottleneck is writing back the aggregates to the key value store, and because Flink internally has a back pressure mechanism, if the sink cannot keep up, then it will just back pressure and will decrease the throughput, and data is going to stay longer in Kafka. So in that case, it would, the concrete number here is, I think, somewhere around 280,000 elements per second. That was as much as we could get out of the key value store with that particular setup. You could probably expand this by building in some manual sharding logic against multiple Redis nodes and so on. I mean, even if you take this times 10 or so and use for the key value store even more resources than we use for the stream processor, then you can still see that you may be able to get somewhere here or so, but you're still far away from what actually the stream processor can do. So It turns out that in this particular application, this communication between the stream processor and the database is really the biggest bottleneck. And that's actually interesting because if you look at what many of these benchmarks actually do these days, they're just like benchmarking the hell out of a stream processor in a kind of simple use case, right? And for many real-world applications, that's not really quite helpful because the bottleneck is often not within a system. Within a system, you can make sure all the parts play together very well. But as soon as you have systems that need to interoperate and communicate, then you're hitting completely different bottlenecks that not an individual system can just optimize the hell out of. So how can we actually work around that? Because it doesn't really make sense to build a super scalable and performant stream processor and allow this to scale out very far if in the end, you're going to pay all the performance anyways when you're trying to do remote updates on a database. So that's kind of the motivation for what the main theme of this talk is, queryable state. So in a nutshell, the idea of queryable state is actually that simple. It just is, instead of saying the real-time aggregates, we're going to pick them up from Redis or any other database, let's pick them up directly from the stream processor. Why not, right? So the stream processor apparently has them stored internally somewhere. They're the windows, the hourly windows. You have the counts per key and so on. So they're there. We just need to expose them somehow. And that is pretty much in this prototype exactly what we did. Real-time queries, in this case, we're going directly against Flink, basically, and not against Redis anymore. If you wish, there's an optional, still, flush the windows at the end of the hourly period or so into some archive database. And, as soon as they're immutable, you basically do only one write anymore, a put. And, and then you can actually, reduce the amount of data you're keeping inside the stream processor and just say, all older queries go against the database, all real-time queries go against the stream processor. So this architecture is, in some sense, what this prototype that we did together with someone at Twitter in a Hack Week project actually implemented. And it, like in their architecture, it fitted very well because they really bought into this concept of lambda. So there's going to be a slow path on something based on MapReduce anyways that writes to our archive database, and there's going to be a fast path based on, in their case, it is Heron and some key value store they built internally that they used for the real-time queries. So they kind of had this idea that they would route queries either to the results of the slow path or to the fast path based on how recent is the result I want to pick up. So that actually fit very well. The real-time queries would go against the Windows, the old database, the old queries, or queries that refer to data that's further back in the past would go against the archive database. So this extension was actually something that is conceptually was very easy to build into Flink, and there are a few corner points that I want to highlight why we could actually do this, and why haven't stream processors been doing this all along? It seems like such a natural thing to do. This is such a severe bottleneck, and why not just immediately pick up the data from the stream processor? So there's a few things that stream processors didn't have for quite a while, which is actually quite important if you want to realize something like that. And the first thing is actually that the stream processor has to be aware of state and have state as a first-class citizen. If you look at Storm, I think prior version 1.0, which just came out, it didn't even have a concept of state that the stream processor was aware of. The state by itself also has to be fault tolerant. It's not just about replaying events, but the state itself has to be recovered with good semantical guarantees, like exactly once. The state also has to be partitioned and scale out with the operator. So it doesn't make sense to have the state in one centralized instance and scale out the computation. So the state has to actually scale with the computation, like you would start sharding a database and scaling it in and out if your state grows, right? Because that's how you actually make it scalable. The next thing is if you actually want to expose something like a database from within a stream processor, it becomes a very tough thing if you actually do this based on a mini-batch system. It's much more straightforward if you do it based on a system where actually operations live continuously, like a proper continuous stream processor. And the last part is that it's fine to say I keep state initially in memory, but if you actually want this to work reliably, you really would like to, have the characteristic that each node can store data in memory, but also on disk if the memory becomes scarce. So all of these things are things that Flink state mechanism actually offers, and why we could actually build this in there. The current state of Queryable state is it's not yet in any full release. There's an open pull request. It's for Flink 3.779. It is you can actually check out this pull request, run a job, instantiate a query client, and actually issue some queries and do some experiments. The exact design and implementation are a little bit under evolution, so we're still trying to tune here and there a bit to see what works best. Because actually this is going on all the time, there's a little caveat. So most of these experiments here were actually done not with the exact version of the pull request, but with a bit of an earlier version, a slightly different implementation. So the exact numbers may vary a little bit, but the important thing is of the ballpark, which is the same. And yeah, so it's still under evolution and work in progress. I guess the most interesting question is, does it actually solve the performance problem? And if we actually rerun this whole implementation with Queryable state on 1 million keys, then yeah, what we actually see is it does solve the problem. And it's actually not surprising that you get the exact same throughput as you used to get before, because assuming that in the 100 keys case, there's really no bottleneck in the interaction with the key value store, in the Queryable state on the 1 million keys case is also no bottleneck in the interaction with the key value store anymore, because the data is simply not written every second, right? It's just kept in Flink, and it's kept in the exact same way as it is kept anyways by the window that computes. So there's really literally no overhead here. The applications have to, like I mentioned, sort of adjust a little bit to this paradigm. If you have an application that's only interested in the latest real-time results, let's say you just have a dashboard and you want to see the state of what is currently going on, then the only change that you really do is, instead of using a Redis client, you use the Flink Queryable state client and basically send your queries directly against Flink. If you have a system that is really interested in both the latest and older results, then you have to do something that's a little more elaborate. You sort of have to work with something like a query service or so. You have to make your application aware that there are kind of two different parts where you can pick up results: old results and up to the second results. So this, like I mentioned, this doesn't seem apparently. When I first thought about this, I thought it was very exotic. But I've actually since seen a bunch of companies, everybody that bought into this idea of the Lambda architecture, that actually have something like this query service actually in place internally, anyways. Precisely to sort of make applications switch between the results computed by the fast path and the slow path of the Lambda architecture. So what you get here is you still get a lot of the benefits of the Lambda architecture in terms of you don't have of not having the Lambda architecture. I'm sorry, you don't have to have the stream processor and the batch processor. You literally have one thing only. You just have to slightly direct your queries different ways. I'd next like to look a little bit in how does the Queryable state in Flink how is it exactly implemented in Flink. And before I dive into this, let me quickly do a brief review of the architecture of Flink, so that would make the next part a bit easier to understand. So Flink has, if you wish, two big types of processes that are running: the job manager, which is the master, and the task managers, which are the workers. And then there's the client side, which runs the Flink program, really the functional program that I showed on one of the first slides. And where this program is inside the client is executed, transformed into the data flow graph, and sent to the cluster. Once it has arrived in the cluster in the master or one of the masters in a high availability case, the master is going to have a data structure called the data flow or execution graph, which is a representation of the parallel data flow of the program. And it basically uses this to schedule and to track progress and to sort of detect failures, figure out what needs to be recovered and how. And it sends to the task managers, to the workers, calls to execute certain tasks. The task managers then execute the tasks in their resources. There's a network manager which handles streams being exchanged between task managers. That handles all the things like stream multiplexing, establishing connections and tearing them down, and so on. So with Queryable state, there are actually two pretty lightweight components that we added to the system. Most of the logic is actually in the query client. So the first thing is that the job manager has an interface that basically lets you ask where a certain resource is currently executed. So let's assume that we want to access the state of a certain job, a certain operator. So job would be the ID or name of the tweet impression job. The operation would be hourly window. The state name in this case would be, in Flink operators can have multiple types of state, also user-defined states. So in this case, it would just be the window state, and then the key would be the key of your tweet, right? So that's kind of the query that you want to send. And the first thing that it would do is it would actually send a lookup to the state location server, which would look into the execution graph, which is integrated with the scheduler and is aware where is this thing executed right now. And would tell the query client where to find it, and then this would actually look at the state registry where operators register all their local state that they have and that they want to expose, and the query client would just pick it up from there. So it's kind of a I think fairly straightforward thing, right? First you actually look up the location, and then you directly query the location. The query client does some caching, so not every lookup has to actually go to the job manager again. And that's actually basically it. There's a bit of a retry policy, so in case something actually failed and was scheduled somewhere different, then the task manager is going to respond with, nope, that's actually not here, and it basically trigger another lookup and say, okay, then tell me where it is now, and then you do a second lookup where the state actually is. But that's basically all there is in this implementation. So it's kind of a, if you wish, lightweight add-on to what Flink is. So why is this actually now so fast? So what is it doing fundamentally differently internally than what, for example, Redis or Cassandra would be doing? Why is the putting to a key value store, just completely aside from the fact that you have to send some network packets if you put something into a key value store that's on a different machine? What is the very fundamental difference? Why you're actually getting such a high performance here compared to just interacting with another key value store? And that is what I want to talk about next. So while diving into this, the first thing I have to do is actually give a little credit. If you've been here at Buzzwords a couple of times, you'll actually have seen this guy speaking a bunch of times, Martin Kleppmann, about turning the database inside out. And he's been speaking about how you can actually rethink this paradigm of databases which log and then write into tables into something different. He was mainly talking about data warehousing with Kafka and Samza, I think, in these talks so far. I am actually going to pick up some of his views and terminology to just explain why this architecture actually gets this nice performance. So in some sense, you could actually think that what this queryable state in Flink is doing is this turning the database inside out ++. So I would view it as the natural next step from this kind of ideas. So to understand what is actually working so differently, let us just look at some key value store that is actually offering a good amount of durability, persistence, and consistency that's very popular out there, Cassandra. The write path of Cassandra in particular. So if we actually write data, the first thing that will actually happen is that the data goes to a commit log. Every time you flush your updated counters and put them into Cassandra, the first thing it does, it actually goes to a commit log. Then it goes to a mem table, and the mem table is accumulating data. Once in a while, it's going to be sorted, compacted, flushed, and becomes an SS table. So what we actually see is the first step is about log durability. And that's not only a Cassandra-specific thing. If you actually go through all kind of databases and that offer durability, that's really virtually always the first step. The second interesting thing to notice here is that this mem table per se is actually not a persistent thing immediately, right? System memory, as soon as the process goes down or anything, it's actually lost. But it's not a big deal because the mem table can always be recomputed using parts of the log and some other SS tables. And another important thing is that really durability, it's not considered durable before it has been replicated to a quorum of nodes. And the important parts here, the costly parts are actually writing to the log and doing the replication. Now, if we look actually at our architecture here, one interesting observation is why would we actually want to redo this every time for every counter update that we do, given that our data is actually durably stored in a log already in Kafka. It is logged and it is replicated. And actually, the event stream is anyways our ground truth here. So given that is persistent, that's a huge thing to build on, instead of just having a second system that tries to do the exact same thing again, keeping things available and durable. the queryable state that we have here in Flink, you can think of it as it's really just taking over the role of the mem table in Cassandra, right? It's something that is not immediately persistent. It's really just something that is that is persistent in intervals, like a Flink checkpoint. Think of it as a mem table is persisted on disk as an SS table, but in the time in between, it's recomputed from the event stream from Kafka. So that means that in this architecture, all Flink is really doing is actually the part that is cheap in Cassandra, right? It's not the expensive part. It's only doing the cheap part, and it's actually relying on the cooperation with Kafka to do the expensive part. And Kafka is actually very performant in doing this expensive part because it's not doing a per update replication and quorum and logging and everything. It's really just you write data fast into your topic partition, and the replication is pipelined and everything. So it's not like you're actually tracking individual things. It's very much streamlining this whole durability thing, which makes it very efficient. If we then actually look at what processing is, here's a little cheap illustration. This is basically the job that we're executing. These operations here, the source, filter, and map, and this is the window and the sum. Our data is coming from these log partitions, and the events are flowing through the system. There's some basically virtually stateless stuff happening here. They're flashed to the network, they're shuffled, and then in the window, there's some operation happening, right? You update the counter or your aggregate, and this happens in some form of state index. Let's say it's RocksDB here. That's a very common option in Flink. The persistence path inside Flink actually consists of two things. Triggering a checkpoint is basically an operation that comes for free. The master is just going to tell the nodes it's time to trigger a checkpoint, and the nodes will inject a checkpoint barrier into the stream. A checkpoint barrier is basically a couple of bytes that are injected into the stream. It's a special event. So that is a virtually unnoticeable overhead. The checkpoint barriers actually travel through the stream, and at some point they're going to reach the operators below. There's a little more magic involved. If you have operators with multiple input streams, there's an alignment phase on the barriers and everything. But once these barriers actually reach these operators, all they're going to do is, in the RocksDB case, if you pick the asynchronous snapshot version, they're only doing a metadata operation again. They're saying, okay, here, trigger me a copy on write snapshot. So all you're basically getting is that RocksDB puts a tag. Now it's a log structured merge tree anyways underneath the hood or something similar to that. And changes are anyways appended first. And all it's actually doing is it's saying I'm not compacting into the old versions because I actually need to hold on to these old versions. I'm just updating new versions and compacting new versions, but I'm also going to hold on to the old versions for a while at least. So this is, if you wish, a metadata operation. It's not really costing anything. And then the part where the checkpoint barriers travel through is actually complete. So we have these shadow copies of the state now, and then all the streaming pipeline actually continues processing. It does updates in RocksDB, and there's a background thread that just takes this copy on write view and flushes it to some durable storage completely in the background. It's not really interfering with your streaming computation. So that altogether actually sort of, I think, illustrates while doing the queryable state in a database where you, not in a database, the queryable state in the stream processor can be so much cheaper than actually doing it in a database. And it can actually give you very good guarantees. If you look at this, shadow copy, asynchronous flush trick, it's something that Redis uses in the background. But then again, it doesn't help you a lot there if you want to not lose data, because Redis is not really integrated with the computation and with a log and so on. So it doesn't really have the ability to recover whatever happened in between the flushes. If you actually just do this all in the stream processor and something that is designed to work on a log, to replay, to snapshot in the background, you basically just get all parts working together in a way that they don't impose unnecessary overhead. They don't redo durability work that has actually been done before anyways. So that's basically the whole story, if you wish. The takeaways of this story are the following. I mean, if you completely zone out and didn't listen to anything, then pay attention just to these two slides. One thing that is, I think, very, very interesting to know is that cross-system interaction is frequently the biggest bottleneck. It's often just not in the stream processor itself. One big bottleneck is the communication between the streaming system that is all pipelined and flowing and the key value store, which most key value stores were made for something else, for point puts and lookups and so on, making them immediately visible and so on. If you actually, you can mitigate this bottleneck by just giving a good amount of the key value store row to the stream processor itself. And Apache Flink has very sophisticated support for state, which makes it possible and performant to add this. About Queryable state itself, kind of the secret sauce behind why it's fast is data persistence is very fast with distributed logs like Apache Kafka, which is because it's a specialized thing, right? It's append only, it's streaming replication and everything. So this is just making a sequence of events durable without also making the view you compute over them durable. Just solving this one problem good makes it actually fast. And then the computed state over this view of events is actually very fast in Flink because you can do it just with local data structures and with no synchronous parts, with just completely asynchronous replication. And the checkpointing that we built into Flink actually handles that. That's the main takeaways. Thanks.
Thank you, Stephan. We still have 5 more minutes for Q&A. Anyone wants to go first? Sorry, guys, on the balcony, I will not go there. Okay. So let us go this way.
Thanks for the talk you gave. I have one question to your performance figures. I just wanted to know if this was with a persistence test or just with in-memory. The ones you show, where you showed that the state.
You mean this one here?
This one, yes.
You mean is the bottom row? Is it actually checkpointing or not?
Yes.
It is actually checkpointing. Yeah.
Okay, thanks.
Yeah, thanks again. So once you allow arbitrary clients to query your stream processor directly, how does it affect the stream processing? Because usually you have a predictable amount of consumers and you usually scale your stream processor with the amount of data that flows in, but now you get unpredictable read load.
Yeah, that's actually a very good question. So these figures are basically sort of looking at the write throughput. You're absolutely right. As soon as you're starting to throw in a lot of read queries, the reads and writes are sort of competing for resources, right? If you look at where do we have it? At this figure here, if you're actually making at the same time an update here, and you still hold on to this other snapshot copy, you're ever iterating over it and you're persisting it, there's going to be a little bit of contention for resources. That's absolutely true. So I mean, a very natural follow-up would be to benchmark this, the read and write trade-offs. I think there's going to be a bunch of read trade-offs. I would agree here because at least in this initial version, for example, there's not multiple replicas from which you could actually read, right? This is something that you would have in Cassandra. You have multiple nodes that hold the replicas, and you can, in theory, balance the reads over them. That is not yet happening here. There's sort of a natural follow-up if you wish to let the nodes replicate each other's state, basically coordinated on checkpoints or so, which would give you that, but in the first version, it doesn't have that. The read path, you're also not seeing good numbers or any numbers for the read path in here because that actually is the part that changed the most in our implementation so far. So the first prototype was actually implementing the read path based on akka internally, creating actors that would answer the read queries and so on, so to sort of allow you to integrate this. We didn't want to tie it to akka in the end, so we created a protocol based on Netty for the next version and so on, and all of these have slightly different characteristics. So there's going to be some numbers, but I think we have to converge this a little bit before it makes sense to present something, because the read numbers would actually, I think, change over time with evolution.
Okay.
So I mean, just as a conclusion, I think this is sort of, makes a lot of sense for very write-heavy throughputs. That was basically the scenarios that motivated it and in which we tried it out and in which it worked very well. If you have scenarios which are basically not doing a lot of writes but are extremely read-heavy, we've yet to see. It probably would take some add-ons to make it suitable for that.
Let us take just one more question.
Does Flink also offer authorization for the queries if I have different users to do those queries?
In this first prototype, no, it doesn't. There's a whole thread in Flink going on about security permissions right now. Working with Kerberos, with key tabs, integrating more with Kafka, renewing tokens for Hadoop and so on. I think it makes sense to say this basically should extend to queryable state as well at some point in time, but at this point, no. In the pull request that I showed here, there's no implementation of authorization, encryption, authentication. No.
Okay, thank you. And actually, it is not a prototype, but the production version of lunch waiting for you just outside.
All right.
Thank you very much, and see you in 90 minutes.